Okay, thank you so much. We are going to present our project. We are Team Advocados, and we are Alejandro and Alberto. And we are going to talk about a quantum counselor for portfolio investment. In this case, we want two things. One is forecasting stocks and the price of the stocks. And the second is try to optimize the election of some stocks to have a good profit. About the outline, we have first, what is the quantum neural network and how we use this for forecasting the stock prices. The second is the portfolio optimization cost function and how we solve the different problems that we solve. The third is a novel approach that we use where we change the cost function and find a better profit. And finally, we give some conclusions and future work.
To separate two parts, Q&A forecasting and the portfolio optimization. In the Q&A, we input A stocks. This stock is apply a classical proposition, and we need to normalize, apply PCA or no, and consider in the case to no, the closed variable. In this, we need to now apply a quantum proposition is encoding the variable classical in a quantum circuit. And this obtain certain answers in the quantum network. We involve TensorFlow quantum OpenLN, two frameworks, and the connection this one with a classical model using TensorFlow. And this classical is applied the LSTM, the data optimization, and the mescon error. After that of these results, we input in the QUBO portfolio, cost function, apply the identify the cost function is the diagram, and we need to with this solution identify with these different algorithms. Two in the quantum way is PQB or QAOA. In this way, obtain the output for this portfolio optimization. Next, please. In this part, we are explaining the stock forecast using a QNN. In this case, we are using the classical part is encoding the quantum in angle in the quantum circuit and parametric gates the angles, and the measurement is applying the classical model. Next one. So in this case, we need to work with 8 stocks. These stocks is in different ways, like basic materials, consumer goods, healthcare service, utilities, finance, industry, and technology. This we need to remark is the period of time is in 2012 to 2018. No, 17. Next one. And the encoding is reduced for each instance is 30 days or a month, and we reduce this in 10 qubits. So in the coding is uses the axis y and x. This is in rotation, and after that we are encoding in an axis stance, and is 2 layers. One layer is only with y's and rotation y, and the other is rotation x. So we need to identify the number of the weights or angles. In this case is x0, and after that we are only measure the 10 qubits in the for applying the classical part. Next one, please. So the results of this is using the basic layer is the minimal model in the classical and the hybrid. In this both we use it approximately the same number of the parameters around, and after we are using a classical model with more bigger number of the layers. It's the same with the hybrid model and the same with the noise model. We can see in the or the cyan is the prediction. So for consequence, the red is the real value, and we can see all use the similar proposal, well, the same structure. Next one, please. And we'll only remark in the model, remark is the same, only replace with the parametric quantum circuit. The next one. And we need to remark in this the identify with the metric is mean absolute error. We can reduce with the minimal with one result, and we can see it's practically the same with positive or negative, or positive and negative one into the space in the training test. So practically we are using in the PCA or not using to respect the classical. The next one. And with more layers. This one we are using in IAV with noise and penny lane. So in this increase the number of the parameters, and it's around 2000 in classical, and reduce in the hybrid with 100,000 one, please. In this, use it the same method where we are to the mean of the quantum and classical measurement, and we can solve is practically the same. It's the same structure with the previous one. One error, positive and negative, for this structure. So we can conclude for now this is a good result compared with the quantum layer. The next one, and in the we identify certain problems with the time when we're working with the average model. Using TensorFlow, we are working with 3 seconds, but when we're working with penny length, is approximately 40 times more slow than the software considered TensorFlow quantum for and all the experiments.
Okay, the second part is the portfolio optimization. When we have the forecasting data from this QNN model, we want to try this with 3 simple models. One is the XS. When we have 3 stocks and 2 periods, which means 6 qubits. Model S with 5 stocks and 3 periods, 15 qubits. And model M, 8 stocks and 3 periods, 24 qubits. And all of them are solved using QAOA and BQE with classical optimizer SPSA and QUBO. First, we have to talk about the cost function. We have the return, that is what we want to maximize. We have some risk associated with the stocks and how they vary each one. If they have like some correlation, then the risk is going to increase. We have some part of the transaction cost, and we have a budget constraint when we cannot spend more money than the budget that we have. About we are showing only here the result of the QAOA for the S model and the VQE and how they are the training of both of them. For the QAOA, we see that with SPSA, we have like some variations, and with QUBO, time try to come to the minimum. But in this case, we found like bad result when we only use 1 repetition of the mixer and the Hamiltonian. Then we have to repeat again, and we have 2 repetitions for this. And the VQE is going well, but it takes some time to come to the minimum, but we are only using 50 iterations as a maximum. For the 3 models, we can see the cost function here. That is like the representation that if we are coming to the optimal point, if we compare with CPLEX, that is in this case is giving us the minimum. Then for the case the XS model is going to, for all of them, come to the minimum. For the S model, some of them come and depends on like the initial conditions, but we can go to that point of good results. And even if we increase the repetition of the maximum iteration, we are going to get closer to the minimum point. In this case, QAON and SPSA give me the good result. And for the model M, we can only execute two models with QAOA, and we are running in this moment BQE because we have some technical issues trying to run this in the CASM simulator of IBM. And the third is we came with a new approach for the cost function. We are making the budget constraint weekly if we have a good opportunity to get a good profit and a small risk of the forecasting method, or QNN, that Alberto explained before. And we call kappa. Kappa is the forecasting error associated with the QNN prediction. And this is the mean relative error of the test part of the training of the QNN. Then we include that or another term that is based on this risk associated with the forecasting prediction. Our novel approach gives us better profit than the current approach. Then in this case, in this special case that is the S model, for the first and second period of time, we could make a higher uh, investment, and we are going to get better profit. And we can see here that for the period 0 and 1, we have better profit than the case of the S model, because in this case we are restricting our budget to our budget. In this we can increase for some opportunities of winning our budget, but at the final part we go to the 100% of the budget, because this last period is not as good as the first and second. About the conclusions of future work, for the part of the optimization, we see that we can implement this model of Muhel et al. For the cost function, and we can improve this in some way to get better profit. And yeah, that's.
In the case in the Q&A, we can improve the number of layers to reduce the classical model and increase the number of the quantum part. And we expect to obtain the similar results or improve that results. And then it's all for this project.
And for future work, we hope to increase the number of qubits, or having backend with more qubits, and we will try to make more large problems. And we also want to try this on real hardware. We couldn't because we tried to run them in the IBM quantum backends, but we get some errors, and we have to try to fix them, and we will present some results based on that. Thank you so much for this event. We enjoy really the coding challenge and this hackathon.
Thank you so much.